Okay, in this video we're going to be looking at how to test a claim about a standard deviation or variance. This is the last of the three things that we will be testing a claim about. We've already tested a claim about a mean in one video, and in another video we talked about how to test a claim about a population proportion. Now in this one we're going to be dealing with a standard deviation or variance. We'll look at some of the requirements of testing a claim about a standard deviation or variance, and also we'll look at the test statistic as well. And then we'll look at some of the properties of a chi-square distribution and three examples of testing a claim about a standard deviation or variance. Okay, we'll begin this particular section with two requirements in a testing of a claim in regard to a standard deviation or variance. And there are only two of them. One of them, you must have a simple random sample. In other words, samples of the same size have an equal chance of being selected. Okay, that's the basic definition of a simple random sample. So when you test a claim, you have to have a simple random sample. And then second, this one is going to be very, very important, that the population does have a normal distribution. And this is a very strict requirement. Okay? When we're dealing with a claim about a standard deviation or variance, you must have a normal distribution. Okay? That's very important. And once those two requirements are met, then we can test a claim about a standard deviation or a variance. And the test statistic that we can use, or we will be using when testing a claim about a standard deviation or variance, we're going to be using a chi-square test statistic. And this symbol means chi and then the square. And that's chi-square. And it's equal to the quantity n minus 1 times s squared divided by sigma squared. And let me explain what these variables mean. Okay. Now, as I stated earlier, this symbol right here, that's your chi, so this will be chi square. Okay. And then your n, that's your sample size. The s square, that's called your sample variance. In this case, in some of these examples that we do, you're going to find that you'll be given the sample standard deviation. If that's the case, you'll take that sample standard deviation and square it, because the sample variance is nothing but the square of the standard deviation. And sigma squared, that's going to be the population variance. Now again, you may be given just the population standard deviation, but when you find the population variance, you just take that population standard deviation and just square it. Okay? So that's going to be your test statistic for the testing a claim about a standard deviation or variance. And I'm going to go ahead and put this up here. You can see that there's the formula. And for the p-values, more than likely we're going to be using technology instead of table A-4. Okay? The technology we'll be using is the TI-83 or the 84 plus calculator, because it's much easier to calculate your p-value. Okay? And most of the examples I will be doing will be using the p-value approach, because in the homework you'll be asked to provide the p-value, and your TI-83 or 84 plus calculator will do that for you, and I will show you how to get that. Okay. Now, this right here is the manual calculations with the p-value. Now, after you find the test statistic and the number of degrees of freedom, which is, of course, n minus 1, n is the sample size, the degrees of freedom is that sample size minus 1, then the p-value can be found using a TI-83 or 84 plus calculator. Okay, and the approach that you'll be using is this. You're going to press second and vars to get your distribution menu, and then you're going to select the menu item that says chi-square CDF. And then that chi-square CDF command will require that you enter 3 separate items, and they're going to be separated by commas. Now, if you have the TI-84, then you'll enter each one of them individually after pressing enter. Okay, so for the chi-square CDF, you'll first enter the lower bound, and then your upper bound, and then your degrees of freedom. Now, in this table right here, if you have a left tail test, then for the chi-square CDF, you'll enter for the lower bound negative 999,999, and then your test statistic from step 5, and then your degrees of freedom. Now, for a right tail test, your p-value is going to be this, the chi-square CDF command, and then this time for a right tail test, you'll first enter your test statistic, then your upper bound will be 999,999, and then finally your degrees of freedom. Now, if you have a two-tailed test, then the p-value is going to be the smaller of these two, and that will be twice the value obtained from the chi-square CDF for negative 999,999, then your test statistic and degrees of freedom, or twice the value obtained from chi-square CDF, test statistic 999,999, and then degrees of freedom. Okay? So the two-tailed test might be the one that's going to be a little bit difficult here, because you're going to have to do both of these, if at all possible, and then choose the smaller of the two, and then take 2 times that value. Okay? Now let's talk about some of the properties of a chi-square distribution. Now, all the values of your chi-square are going to be non-negative. Okay? And the distribution is not going to be symmetric. In other words, it's not going to be having that normal distribution, as you can see in this particular graph. It's always going to be skewed to the right. So it's not symmetric. And then second, there is a different chi-square distribution for each number of degrees of freedom. In other words, if you look at this graph on the right, the chi-square distribution for 10 degrees of freedom is this blue graph here. The one that's in red represents the chi-square distribution for degrees of freedom of 20. Okay? So that's the difference there. And then your critical values are found in table A-4 using n-1 degrees of freedom. Now, if you are using the critical value approach, then you can use table A-4. However, the problems that we're going to be doing in this video and on the homework only require the p-value approach. So we'll be using the TI-83 or 84 plus graphing calculator. Okay, so let's look at some examples of calculating or testing a claim about a standard deviation or variance. Let's start off with the first example. And again, we're going to be using that 8-step approach for hypothesis testing, like we did in the other videos before. Okay. So this first example is this. Workers at a certain soft drink factory collected data on the volumes in ounces of a simple random sample of 23 cans of the soft drink. Those volumes have a mean of 12.19 ounces and a standard deviation of 0.11 ounces, and they appear to be from a normally distributed population. If the workers want the filling process to work so that almost all cans have volumes between 11.92 and 12.48 ounces, the range rule of thumb can be used to estimate that the standard deviation should be less than 0.14 ounces. Use the sample data to test the claim that the population of volumes has a standard deviation of less than 0.14 ounces. Use a 0.05 significance level. And here you're going to complete parts A through D below. But here, we're going to use the 8-step procedure, because if we use that 8-step procedure, we can answer the questions that are in this particular problem, A, B, C, and D. So in this case here, let's start off with step number 1. In step number 1, you're always going to state the original claim. You always state the original claim. In this case here, we're testing the claim that the population of volumes has a standard deviation less than 0.14 ounces. So here, standard deviation, which is your sigma, is less than 0.14. And then step number 2, we state the opposite of the original claim. Well, the opposite of less than would be greater than or equal to. So that opposite would be sigma is greater than or equal to 0.14. And then from steps 1 and 2, we can write our null and alternative hypothesis. So this will be the answer to part A, identifying the null and alternative hypothesis. So this is step number 3, which is going to be the answer to part A, your null and your alternative hypothesis. Keep in mind the null hypothesis always has the equality in it. So it's going to be sigma is equal to 0.14, and the alternative is going to be one of these two. It never has equality, so it will have to be the original claim, where sigma is less than 0.14. Now I'm putting the word claim right beside it because that's the claim. So here your claim is the alternative hypothesis. And step number 3 answers part A, identifying the null and alternative hypothesis. Step number 4 is to state your level of significance, or your alpha level. And that's given in the problem. So in this case here, we're using, let me bring the paper down, using a 0.05 significance level. So alpha is equal to 0.05. That's your level of significance. And then step number 5, I'll do this off to the right side. Step number 5 is calculating your test statistic, which is going to be part B, compute the test statistic. Okay, the test statistic for a standard deviation or the variance is your chi-square test statistic. That's going to be equal to n minus 1 times s squared divided by sigma squared. And then we just substitute those numbers into that particular formula. Well, let's identify some of these things here. We have a simple random sample of 23 cans of soda drink. So n is 23. And s is your standard deviation. Now, we don't need the mean of 12.19 ounces. Okay? The mean of 12.19 ounces, that's irrelevant to us. And then we have a standard deviation of 0.11 ounces. That's your sample standard deviation, 0.11. And Your sigma is from your null hypothesis. That's 0.14. So all we can do here is just substitute those values into this equation, or into this formula. So now the numerator is 23 minus 1 times sigma, that's 0.11, and that's squared. Now here, this is just an example of a sample standard deviation that's given to you, so you just take the 0.11 and you square it. And the same holds true with the population standard deviation, that's 0.14. That's going to be squared as well. Okay, and then we can type all of this into our graphing calculator. So in this case here, I'm going to type in left parentheses 23 minus 1 times 0.11, and then hit x squared to square it, divided by 0.14, then hit x squared again to square that 0.14, and then hit enter to get your answer. Now we're going to round this off to 3 decimal places. In this case, it's going to be 13.582. To 3 decimal places, your chi-squared test statistic is 13.582. Okay, and that's part B, computing your test statistic, 13.582. Alright, now step number 6. We find the p-value. Okay, so here we're going to find the p-value. We're using a p-value approach here in this particular problem. So part C is finding the p-value. Okay, we know our degrees of freedom is n minus 1. N is 23, so 23 minus 1, that's going to be 22. Okay, now, by looking at our alternative hypothesis, it's less than. So that tells me I have a left-tailed test. I have a left-tailed test. So that means I'm going to be using, in this case here, in my graphing calculator, the chi-square CDF command, and then my lower bound will be negative 999,999, and then the test statistic, then your degrees of freedom. So in this case here, chi-square CDF, then negative 999,999, comma, the test statistic, which I found in step number 5, is 13.582, comma, degrees of freedom, that's 22. And then I'm going to come up with a decimal value to 4 decimal places. So here, press second and vars. Let me move this up a bit. So here what I did, press second and then vars to get the distribution menu. And then I'm going to select chi-square CDF. And then enter. And then I'm going to start entering. Now, usually I get the parentheses here because I have the TI-84, the older version of the TI-84. The newer versions will give you the lower bound, the upper bound, and then your degrees of freedom listed separately. So you'll enter your lower bound of negative 999,999, and then in my case it's separated by a comma, but if you have the newer TI-84, you have to press enter, and then your test statistic 13.582, comma, 22. And then press enter. Now in this case it's going to be 0.0844. 0.0844. That's going to be the p-value. It is a left tail test, so your p-value is going to be that number. If it was a two-tailed test, then you'll have to do 2 times that. So it'll be 0.0844 for your p-value. So that's the answer to part C, finding the p-value. Okay, now next is step 7 is deciding whether to reject the null or fail to reject the null. This is your decision rule. We're using the p-value approach, so that means if your p-value is less than or equal to alpha, you're going to reject the null hypothesis. So you're going to compare your p-value that you found in step 6 with the alpha level, which is in step number 4. Your p-value was 0.0844. Now we're going to compare that to the alpha level. In this case, that's 0.05. And by comparing those two, you can see that 0.0844 is greater than 0.05. And because of that, this does not satisfy our decision rule, so that means we must fail to reject the null hypothesis. Fail to reject the null hypothesis. And then step number 8 is right now a conclusion statement using simple non-technical terms. So that means if we fail to reject the null hypothesis, that means we are saying that there's no sufficient evidence to support the claim. Okay, and I still have this up here of wording the final conclusion. Our claim was the alternative hypothesis was our claim. We failed to reject the null, so that means that there is not sufficient evidence to support the claim. So here we start by saying that there is not sufficient evidence to support the claim that the population of volumes in soda cans has a standard deviation has a standard deviation less than 0.14 ounces. Right, that's our conclusion statement. Okay. All right. So here you can see how we use our 8-step procedure. Okay. Now in part D, they may have something like, when you state the conclusion, they may say fail to reject the null, and then say that there is not sufficient evidence to support the claim that the population of volumes in soda cans has a standard deviation of less than 0.14 ounces. They may have steps 7 and 8 merged together for part D. Okay. All right. Now here's another example of a claim about a population standard deviation. The piston diameter of a certain hand pump is 0.8 inches. The manager determines that the diameters are normally distributed with a mean of 0.8 inch and a standard deviation of 0.006 inch. After recalibrating the production machine, the manager randomly selects 28 pistons and determines that the standard deviation is 0.0041 inch. Is there sufficient evidence for the manager to conclude that the standard deviation has decreased at the 0.05 significance level, or level of significance, if you want to call it that? Okay, now, here we're going to use that 8-step procedure. And in step number 1, you want to state the original claim in symbolic form. Now let's think about this for a moment. This manager is trying to test the claim that the standard deviation has decreased. In other words, our standard deviation, that the diameters have a standard deviation of 0.006 inches. That's going to be your original claim. So that means sigma is less than. If it's decreased, it means less than 0.006. Okay. And we're using a 0.006 in our original claim, not this 0.0041. That represents the standard deviation of the sample of 28 pistons. That 0.006 is your standard deviation of all of the diameters in those pistons. Now step number 2 is the opposite of the original claim. Well, the opposite of 0.06, opposite of less than 0.06, so it had to be greater than 0.06, so it would be sigma is greater than or equal to 0.006. And then step number 3, we can write our null and alternative hypothesis from steps 1 and 2. The null always has the equality in it. So the null has to be sigma is equal to 0.006. The alternative hypothesis does not have equality in it. So between these two, the original claim where you have sigma is less than 0.006 must be your alternative hypothesis. Okay. Now step number 4 is stating the level of significance. In this case here, we're at the 0.05 significance level. So there's your alpha level right there, 0.05. Okay. And then step number 5 is calculating the test statistic. So step number 5, we have N, which is 28 because the manager randomly selected 28 pistons, so N is 28, and he determined that the standard deviation of those 28 pistons was 0.0041. And I'll go ahead and write down sigma, which is from your null hypothesis, 0.006. And by the way, let me go back to step 3. Your alternative is your claim. Because the original claim has sigma is less than 0.006. So in this case here, the alternative will be your claim. Now back to step number 5. We can calculate that test statistic. That's your chi-square, and that's equal to n minus 1 times s squared divided by sigma squared. So in this case here, we just substitute. We get 28 minus 1 times s, which is 0.0041, and that's going to be squared. Oh, that's divided by sigma, which is 0.006. And that's going to be squared. Okay. So here's where we use our calculator to calculate this. And clear this out. And left parentheses, 28 minus 1, close parentheses, times 0.0041. Then hit your x squared key to square the 0.0041, and that's divided by sigma is 0.006, and that's going to be squared. Okay. Now, if we were to round that off to 3 decimal places, this will be 12.608. 12.608. That's going to be your test statistic. That's your chi-square test statistic. Okay. Now step number 6 is finding the p-value. Now in the homework you will be you will be told whether to find the p-value or the critical value, but here we're going to find the p-value. Alright, now let's look at our alternative hypothesis here. It says sigma is less than 0.006. Less than tells me I have a left tail test. So, to find that p-value, it's just simply going to be that chi-square CDF. My lower limit, or the lower bound, is negative 999,999. Then the upper bound is your test statistic of 12.608. Now, for my degrees of freedom, that's n minus 1. Well, n is 28, so 28 minus 1 will be 27. So my degrees of freedom will be 27. Okay. Now again, for those of you who have the newer version of the TI-84 plus calculator, TI-84, you have to enter this, and then press enter the test statistic, and then enter, then your degrees of freedom, and then enter for your chi-square CDF. So here, second vars to get your distribution menu, second and vars. Then hit your down arrow key for your chi-square CDF. Well, went too far. Chi-square CDF. And then your lower limit will be negative 999,999. In my case, it's going to be a comma, but for you, it will be enter if you have the newer TI-84. And then your test statistic, 12.608, comma, or enter, and then 27. And then enter, because they'll tell you to calculate. Then hit enter. Let's see, the 4 decimal places, that will be 0.00. Actually, the 3 decimal places. And this is dependent upon what the instructions say in the homework. In this case, it's going to be to 3 decimal places, so it'll be 0.008. So my p-value is 0.008. Okay. Now do pay close attention to the homework on how many decimal places they ask you to round off. If they say round to 3 decimal places, then you round to 3 decimal places. Or if it says 4 decimal places, you round to 4 decimal places for your p-value. But in this case, your p-value will be 0.008, rounded to 3 decimal places. Step number 7 is your decision rule. We're using a p-value approach, so my decision rule for the p-value is this. If your p-value is less than or equal to alpha, you simply reject the null hypothesis. If the p-value is less than or equal to alpha, you reject the null hypothesis. My p-value is 0.008. My alpha level from step number 4 was 0.05. If you compare those two, you can see that 0.008 is less than 0.05, and that does satisfy our decision rule, so we just simply reject the null hypothesis. So here we reject the null hypothesis. If we reject the null hypothesis, then that means that we are saying that there is sufficient evidence to support the claim. Okay? So the claim was the alternative hypothesis. We reject the null, so that means that there is sufficient evidence to support the claim. So in step number 8 is the conclusion, which is that there is sufficient evidence to support the claim that the standard deviation of piston diameters have decreased. Okay. So that's our decision that there's sufficient evidence, or conclusion that there's sufficient evidence to support the claim that the standard deviation of piston diameters have decreased. Okay. Okay. So that's pretty much the process of the 8-step hypothesis procedure for a standard deviation. Okay. I'll do one more. Alright, in this case here, a simple random sample of pulse rates of 60 women from a normally distributed population results in a standard deviation of 11.8 beats per minute. The normal ranges of pulse rates of adults is typically given as 60 to 100 beats per minute. If the range rule of thumb is applied to that normal range, the result is a standard deviation of 10 beats per minute. Use the sample results with a 0.10 significance level to test the claim that the pulse rates of women have a standard deviation equal to 10 beats per minute. Again, we'll use the 8-step procedure to answer parts A through D below. Okay. Steps 1, 2, and 3 will help us answer part A, identify the null and alternative hypothesis. So let's start off with this. In step number 1, we want the original claim. And in this case, we're told that the pulse rates of women have a standard deviation equal to 10 beats per minute. So here, sigma equals 10. That's your original claim. Step number 2 is the opposite of the original claim. In this case here, the opposite is this. The opposite of equal to is not equal to. So sigma is not equal to 10. That's the opposite of the original claim. Then step number 3. From steps 1 and 2, we can write our null and alternative hypothesis, which will answer part A, identifying the null and alternative hypothesis here. The null always has the equal sign in it, so that's going to be sigma is equal to 10, and that's also the original claim. So I'll write the word claim next to that statement in symbolic form. The alternative does not, so not equal to 10 will be your alternative hypothesis. Okay, so that's your null and your alternative hypothesis, which is the correct answer to part A. Now, step number 4 is your level of significance. We're told we're dealing with a 0.10 level of significance, so that's given to us in this problem right here. So here we're using the sample results with a 0.10 significance level. So that's your alpha level right there. So step number 4, alpha is equal to 0.10. Now step number 5, calculate the test statistic. And in this case here, I'm letting n be 60 because we're dealing with a simple random sample of 60 women with their pulse rates. And those pulse rates have a standard deviation of 11.8 beats per minute. That's given to us in the problem. So let me pull this back up and you can see 60 women That's your sample size. The standard deviation is 11.8 beats per minute. That's for that sample. Okay? And sigma is from the null hypothesis. That's your 10. So in this case here, your chi-square test statistic is n minus 1 times s squared divided by sigma squared. N is 60, so that's 60 minus 1 times s, which is your sample standard deviation. That's 11.8, and that's going to be squared. And sigma is your 10, so that's 10 squared. And then, using our calculator, let's see, left parentheses, 60 minus 1, close parentheses, times 11.8, and that's squared, divided by 10, and that's squared. Then hit enter. And in this case, you're going to get 82.152 rounded to 3 decimal places. So this, your test statistic is 82.152. Okay, so that's your test statistic there. And by the way, that right there represents the answer to part B, computing the test statistic. So step number 5 is the answer to part B. Okay, now step number 6 answers part C, and that's calculating the p-value. Okay, now, first of all, our degrees of freedom is n minus 1. N is 60, so 60 minus 1, that's going to give us 59. Now let's look at the alternative hypothesis. It says not equal to. Well, that not equal to tells me that it is a two-tailed test. Remember that your alternative hypothesis always tells you what type of test you're going to have, either a left-tailed test, a right-tailed test, or a two-tailed test. In this case, not equal to means a two-tailed test. Okay, so in this case here, we have to follow these directions here. The p-value is going to be the smaller of the following two results, and that's twice the value obtained from this format, or twice the value obtained from this format. Here we're going to have to do both of these in order to find out which one we're going to need to use. We're going to have to use the smaller of these two. Okay? So here's what I'm going to do here. I'm first going to do the chi-square CDF of negative 999,999, comma, the test statistic, which is 82.152, comma, degrees of freedom, which is 59. I'm going to do that first. So here, press second and vars for the distribution menu and hit your down arrow key to find chi-square CDF. And then type in negative 999,999, comma, 82.152, comma, 59, close parentheses. Now I'm going to get a p-value of 0.975, and I'm going to round that off to 3 decimal places. But if I take 2 times 0.975, this is what I'm going to get, 1.950, which would not make sense because the p-value by definition is a probability of getting the test statistic as extreme as the one that we've obtained from our sample data. In this case, probability can never be bigger than 1. So we know that's not going to work. 1.950 would not be the p-value. So let's try the other one. This time put the test statistic first, 82.152, comma, but this time your upper bound is 999,999, and then your degrees of freedom is 59. Okay, so again, using the calculator, we press second and vars, and then hit your down arrow key to find chi-square CDF. This time 82.152 goes in first, and then your upper bound is 999,999, and then 59 degrees of freedom. And in this case, this will be 0.025 if we were to round that to 2 decimal places. But now, let's take 2 times 0.025. I'm going to get 0.050. This is the one we'll use. Okay? Here we're using a smaller of the two. Okay? And 0.050 is the smaller of these two p-values here. So here, your actual p-value will be 0.050. Okay. So as you can see, you have to do both of these, and then take the smaller of the two with a two-tailed test. Now, step number 7 is your decision rule. Now the decision rule is this: we're using a p-value approach, so if your p-value is less than or equal to alpha, reject the null hypothesis. Now in this case, the p-value was 0.050, and the alpha level was 0.10 from step number 4, if you recall. Here's step number 4, and that alpha level was 0.10. Compare those two, you'll see that your p-value of 0.050 is less than 0.10. That satisfies the decision rule, so we say we can reject the null hypothesis. Okay? Our claim was the null hypothesis, so here that tells me that that there's going to be sufficient evidence to reject the claim. Okay? Let's take a look here in wording the final conclusion. The claim was the null hypothesis. We're rejecting that null, so that means that there's sufficient evidence to reject that claim. So in step number 8, we say there is sufficient evidence to reject the claim that pulse rates of women have a standard deviation equal to 10 beats per minute. Okay. Okay, so that's our conclusion for this particular problem for pulse rates of women. The claim was that they had a standard deviation equaling to 10 beats per minute. We found out that we were able to reject that claim, so we can conclude that there is sufficient evidence to reject that claim, that pulse rates of women have a standard deviation equal to 10 beats per minute. Okay? Alright, so this will conclude this particular video on how to test a claim about a standard deviation or variance. And best of luck with the homework.